Hello, I hope you are doing well. Today, I would like to talk about closed-loop supply chain network design problem and introduction to the tire recycling and manufacturing in the tire industry. Uh, Today, I will provide a basic optimization problem and how we can code and solve it. Uh, so let's start. So uh, The closed supply chain network design aims to coordinate the tire recycling and manufacturing into the forward and reverse supply chains. Today we focus on tire industry and we first motivate this problem and we define the problem conceptually and how the physical network is defined and what are the supply echelons and the elements of the problem. And we define a basic mixed integer program to the closed-loop supply chain network design problem. And finally, I will also provide a coding example to how we can formulate and code this optimization problem in GAM software. To motivate this problem, I should highlight that unfortunately in developing countries, many waste tires polluted the environment. Only around 20% of scrap tires in developing countries like Iran will be collected, recycled, and manufactured. However, in developed countries like Canada, around 98% of scrap tires will be recycled and remanufactured. However, yeah, because of demand markets in developing countries like Iran, due to the rapid urbanization of the cities and also uh, a very high rate of cars for transportation. Therefore, uh, there is a very great growth in the demand markets for a tire industry. So there is a need for tire recycling and manufacturing to not only improve economic benefits from the tire markets, but also help the environment to remove the pollution and also increase sustainability into the supply chain. So, to define a physical network, we should highlight that the physical network is divided into the forward flows and reverse flows. In the forward flows, the flow starts from the suppliers who are responsible for providing raw materials, and then the raw materials are transferred to manufacturing centers, and manufacturing centers are responsible to create tire products, and the tire products are then transported to the retailers for distribution of tires to the markets. And markets are demand points, demand nodes in our physical network. And the collection centers in the reverse logistics are responsible for collecting the waste and also scrap tires from the customers from the markets. And then they are will be transferred to recycling centers for recycling and classifying the recycled tires based on their quality for remanufacturing or secondary markets or their industrial examples. In the proposed problem, we contribute to the two different types of decision making. In strategic planning, we contribute to the facility location planning to select which facility at which echelon will be open. So therefore, we contribute the facility location for manufacturing centers, retailers, collection centers, and recycling centers. And from the tactical planning, we compute the allocation of flows for materials, for tire products, and also for the scrap tires and waste and recycled tires between the facilities to define the right amount of allocation between the facilities in different echelons. Uh, Suppliers are independent entities that uh, supply the raw materials. Here we define the notation S, where each S uh, is for the set S capital, and this set defines the set of suppliers. From the physical network, there is a distance between the suppliers and manufacturing centers that show the distance between these locations. And there is also unit transportation cost to show that the transportation cost per unit of the materials which are transferred from suppliers to manufacturing centers. And this unit is varied according to the transportation modes and vehicles capacity. And the manufacturers must purchase the raw materials at a price PSCS, which represent the price of raw materials. And each supplier has a capacity S US, which represent the amount of supplier capacity to produce raw materials. And based on this capacity, they can transfer and the manufacturer centers can purchase the raw materials from the suppliers. There are a set of manufacturing centers who are responsible for tire manufacturing and remanufacturing. Here we represent them by the set M. From a strategic planning view, among a set of potential sites, we want to locate a subset of facilities to be open. In this regard, there is a parameter as a fixed opening cost for installation, for opening, and each manufacturing center. And from the tactical planning, each manufacturing has a predefined capacity for manufacturing and also a predefined capacity for remanufacturing. And there is also a manufacturing cost, which is varied per unit. So there's a unit manufacturing cost for manufacturing the tires, for producing the tires. From the physical network, there is a distance between manufacturing centers and retailers, which represented by this notation here. And also there is a unit transportation cost for transportation of the produced tires from the manufacturing centers to the retailers. And this rate is varied according to the transportation modes in our closed-loop supply chain. There are sub-retailers, which these retailers are responsible for tire distribution. And from the strategic planning point of view, among a set of potential sites which have been considered for retailers, each site has a fixed opening cost, and we want to locate the optimal locations for the retailers. From tactical planning, there's a distribution capacity for each retailer, and there's a unit distribution cost for distributing each tire in the network. And from the physical network, there is a distance between retailers and the markets. And there's also a transportation cost per unit of distributed tires in our network. Markets are the demand nodes, where each node represents a geographical zone in our problem definition. And each market has a demand volume, which can be estimated and approximated. And it is assumed that in each planning horizon, this there is a pattern for the demand market, which can be forecasted. And we also assume that the demand is splittable. It means that we can allocate each market to multiple retailers to satisfy its demand. And it is estimated only a fraction of waste and scrap tires can be collected for the recycling from each market. And from a physical network, there is a distance between the markets and collection centers. And there is also a unit transportation cost for transferring the um, demands uh, from the collection centers from the markets to the collection centers. And the collection centers here are responsible for collecting, sorting, and classifying waste and scrap tires from markets. And from a strategic planning point of view, there are a set of potential sites for collection centers, and we want to find the optimal location. And there is a fixed opening cost for each potential site. And from a tactical planning point of view, there is a predefined capacity for each collection center, and also there is a variable uh, collection cost, which represent the cost per unit of waste tires, which must be collected, the cost per unit for collection. And from a physical network, there is a distance between the collection centers and recycling centers in the network. And there's also transportation cost represents the transportation cost per waste or scrap tire, which must be transferred from the collection centers to recycling centers. And recycling centers are the heart of the closed supply chain, where make this supply chain network to be closed, and also to have a circular economy for to have benefits from recycling. From a strategic planning point of view, we have there's an assumption that among a set of potential sites for the recycling centers, we want to focus on the location of the recycling centers, and there is a fixed opening cost associated with each potential site. And from a tactical planning, there is a capacity for recycling, and there is a unit recycling cost for recycling each scrap tire. From the physical network, there is a distance between recycling centers and manufacturing centers. And also there is a transportation cost per recycled tire for transferring from recycling centers to manufacturing centers. And it is estimated that only a fraction of recycled tires can be transferred for remanufacturing based on their quality. And these revenue associated with each recycled tires, which can be considered for remanufacturing. And there is also revenue associated with each recycled tire, which can be considered for the secondary markets. Therefore, these benefits are from recycling and can be considered in the closed-loop supply chain. To make mixed integer program, we have a set of assumptions which are very common in a closed supply chain network design problem. The first one is that there is no flow between the same facilities in the same echelon. It means that there is no flow between the manufacturers. It means that we have only flow from suppliers to manufacturers and from manufacturers to retailers. There is not a flow between the same manufacturing centers. And for some of facilities like manufacturing centers, retailers, collection centers, and recycling centers, we want to contribute to the facility location planning, where among a set of potential sites, we want to open a subset of them, and there's a fixed opening cost with a predefined capacity for each facility. And the transportation costs are based on two factors: the geographical distance and the transportation cost per unit. It means that for transporting, we must consider the geographical distance between the facilities and also the unit of amount of transferred products and the modes of transportation. So they have different options for transportation costs. And there's also an assumption that highlight that all the parameters here are known and deterministic. And we also assume that only a portion of scrap tires at each market should be collected, and the recycled tires are classified based on their quality. Therefore, there are some revenue associated with the recycling tires. Therefore, they can be sold to the manufacturing centers for remanufacturing or secondary markets for other industrial applications. And in a closed supply chain, we have no control, or we have no entity that can be controlled for the location planning of suppliers, markets, and secondary markets. Therefore, these centers are independent entities and are not owned or managed by the closed supply chain managers. To build the optimization problem, we have a set of binary variables that highlight that which facility can be open from the manufacturing centers, from retailers, from collection centers, and from recycling centers. And there are also a set of uh, non-binary variables, which are continuous variables for amount of quantity for the transportation between the facilities. For example, the quantity of raw materials from suppliers to manufacturers, the quantity of tires transported from manufacturer to retailer, and some other variables which have been defined here. The objective function here in this very simple example is to minimize the total cost. So the goal is to minimize the total cost, which have three items: the fixed opening cost of facilities, the variable cost includes the price and variable cost and the unit cost associated with each center. In addition, the revenues associated from recycling. And there are also transportation costs, where for transportation, there are two factors, including geographical distance, also transportation costs, and the amount of materials transferred. So based on these three items, we make the objective function. A very common constraint in any closed supply chain are network balance constraint. This constraint show that the amount of inputs and outputs at each center must be equal and have the same. For example, for each manufacturing center, amount of all raw materials which have been supplied must be transformed to the uh, tire produce tires which has been distributed to the retailers. And the same logic is applied for retailers, for collection centers, and also recycling centers. And these are the common network balance constraint to show that at each node we must have a control and also balance between the inputs and outputs at each center. We have demand satisfaction constraint that highlights that all the demands must be satisfied. Therefore, the demands from the markets, from the forward supply chain must be satisfied. And we also assume that only a fraction of these original demands will be considered as a waste, and they will be collected uh, in reverse logistics as given in the constraint number 10. And for recycling and manufacturing, there is an assumption that only a fraction of the recycling tires can be sold for remanufacturing. Therefore, here this assumption is modeled. And we have the capacity constraint, which are the main constraint and also make this network design problem complex as the most complex constraint. So we have a capacity constraint for the suppliers, for manufacturing centers, for retailers, for collection centers, and recycling centers. And we have the domain of variables for binary variables and also the flow variables. Uh, Now, I want to uh, share an optimization uh, to model and to code this optimization problem. So here it is a GAM software, and we first define the set of suppliers, manufacturing centers, retailers, markets, and collection centers. And here's a numerical example that shows the number of the suppliers, the number of potential sites for manufacturing centers, retailers, the number of markets demands, and also uh, collection centers and recycling centers. I created an Excel file where at each sheet, these parameters have been defined, and you can see the parameters from the demands point, distance parameters, transportation parameters, and also fixed opening cost uh, of parameters, the fraction of the collected waste from the markets, and also the fraction of the recycled tires for remanufacturing, the price, the capacity, and the variable costs. In the GAM software, we then need to call these parameters. All these parameters must get their value. And after that, we define the variables. So for the variable, as similar to the optimization problem that we have a variable z, which is the objection function, and three variables for calculating the fixed opening cost, variable cost, and transportation cost. In the same way, we have the variable objective function, which is a free variable, and so the positive variable, which is are these variables, and the flow variables, which are here. And we have four binary variables which are defined here, and the equation. For equation, we have defined them similar to the given opposition problem. We have the objective function and constraint 2 to constraint 17. And we can see that for first write the objective function and write each constraint similar to the given in the optimization problem. And for example, these are for the objectives. Here, they are the constraints for the network balance. These are the constraints for the demand satisfaction. This constraint is for the recycling, the tires, and also these are the capacity constraints. that we have here. And finally, we provide the option for using the software. Here we have used a CPLX solver and a time limit of 3,600 seconds. Now we run this optimization problem. As you can see, it first calls the data from the Excel file, and after calling the data, it starts solving the model. Since it is very small example, including a very few facilities, you can see that the optimal value is found in a reasonable time around 20 seconds with a gap around 6% from the GAMS software. And we also can see the variable of the values of the variables. For example, for the manufacturing centers, these three centers are selected to be open. Selected number one, two, and center number six. And for the retailers, for collection centers, and also recycling centers, we can see which center has been open. All other details from the variables and also their feasible variables are defined. And this is the end of my presentation. Thank you for your time. If you have any questions from this paper, from this presentation, you can ask me. And I appreciate your time. And let's keep in touch. If you have any question related to the closed supply chain, I'd be happy to answer. Thank you so much and have a great day.